Okay, today we're looking at exponential growth and exponential decay story problems. Our learning targets today are that we will be able to model real-life situations with exponential growth and decay functions, that we will be able to evaluate exponential growth and decay functions with given values. Exponential functions are functions that can be used to model, exponential functions can be used to model real-life situations. They can be used for representing increasing characteristics, that's an exponential growth model, or decreasing characteristics, that would be an exponential decay model. So let's look at two different situations. If you were to put $100 into a bank account when you were 18, and the bank agrees to give you 5% interest yearly on your $100, find out how much money is in the account after 1 year, 2 years, 3 years, and 4 years. So the way that interest works, if you leave that money in the bank, the first year you're just earning interest on your principal amount, your $100. The second year, you would earn $5 in interest. The second year, you're going to earn interest on your principal, your $100, plus you're also going to earn interest on the $5. So you're earning interest on your principal, and then you earn interest on your interest. And then the third year, you'd be earning interest on your principal plus interest on your interest on your interest. So that just has this snowball effect where each year you make more than you made the previous year. Okay? So let's go ahead and represent this with just a table, and we'll calculate it by finding 5% each year and adding that on. So X is our time, Y is our amount of money. Okay, when we start, 0 years have passed. How much money do we have in our account, boys and girls? $100. Now, how do I express 5% in my calculator? It's so 5% means 5 per 100, cent means 100. Okay, so 5% as a decimal is 5/100ths, or 0.05. So if I want to know how much this will be worth in 1 year, I take my principal amount, or the amount that I had the previous year, in this case it is the principal, and I multiply that times 105%, because I'm going to get all 100% of my money that I put in, plus 5% more. So it's times 105%. How do I do that in my calculator? Well, if I want to put that in my calculator, it's 100 times 1, that's the whole $100, 0.05, because 5% is written as 5/100ths, or 0.05. So I take my $100, I'm going to get all that, so that's times 1, that's itself, and then an additional 5%, so it's times 1.5%. So I'll have $105 after a year. Okay, then a year after that, at the end of the second year, okay, I'll be earning interest on my $100, and I will also be earning interest on my interest. Okay, so I'll be earning interest on the $5 as well. So I'll leave my 105 here in my calculator, and I'll just press my times button. So that gives me my previous answer, which is the 105, times 1.05 again. So we see this repeated multiplication, and we've been working with exponents, so we're very familiar with this concept that repeated multiplication of that same number, it's a power. So we're actually looking at powers of 1.05 right now. So at the end of the second year, how much money do I have in my account? $110.25. Then I'm going to earn interest on my $100, I'm earning interest on my $5, and the interest on the $5, right? And the interest on the $5.25 here. So I'm earning just compounding interest. So at the end of the third year, I'm earning interest on all of the $110.25. So I take all of that, $110.25, times 0.05. How much will I have at the end of the third year? 115.76. Good. And we're not going to round this yet, because when we're working with powers, they actually can grow very quickly depending on what the power is. So we're going to not round until the end when we're working with powers. It's good mathematical practice not to round until the end of any problem. Okay, so let's leave it as 115.7625. If that messes up your table, just adjust it. And then at the end of the fourth year, I'm earning interest and all of that. So at the end of the fourth year, this will be worth, and that's as far as they asked us to go, 4 years. Okay. So this is representing our money. Now, if we write it in, it's because it's representing money, we would round these to the nearest dollar. Okay, so at the end of the first year, how much was this worth? $105. At the end of the second year, how much was this worth? $110.25. At the end of the third year, how much is this worth? $115.76. Now we do round, and then at the end of the fourth year, $121.55. Okay, now what if I asked you to find out how much money this will be worth in 250 years? Would you like to extend this table out to 250? No, I wouldn't either. So there has to be a better way mathematically to represent this, and that's what the exponential growth formula does. So we're going to learn about that today. And then we'll also learn about an exponential decay formula so that we don't have to extend that table. You can just let x equal 250, and you can find out how much that will be worth at the end of 250 years. Okay? Not that you'll be around to spend it, right? So then let's look at situation 2. In the city of Detroit, 10% of the people have left the city every year since 2010. I don't know if that's exactly accurate, but let's just go with that problem. So it is definitely, there's declining population in the city of Detroit. I don't know if that trend has changed recently, but that definitely was a trend in 2010. So 10% of the people have left the city every year since 2010. In 2010, the city's population was 600,000 people. Find the population for years 2011, 2012, 2013, and 2014. All right, so the starting point is 2010. Yeah, so the starting point 2010, we're going to call that year 0 because that's our starting point. So 2010 corresponds with 0. 2011 will be 1 year all the way up to 2014. Okay, so we want to remember we're not going to be putting, when we get to the formula, we're not going to be putting these numbers in. We're looking at elapsed time, or time that has passed. Okay, so in the beginning, in 2010, and we can write it in 2010, or year, you can call it year 0. I'll put a 0 up here. That's my starting point. Can you get that, please? Thank you. Okay, so in the beginning, our population was 600,000 people. Okay, and then it's declining enrollment. So after the first year, we have 10% of the people left. If 10% of the people left, what percentage of the people are remaining? Good, 90%. So I want to know what 90% of 600,000 is. So I'm taking that 600,000 and I'm multiplying it by 90%. In my calculator, 90%, 90 per 100, 90 hundredths, right? So that's 0.9. Okay, 90 over 100, 0.9. So I'm multiplying that by 0.09. Or excuse me, 0.9, pardon me. So 600,000 people times 90% times 0.9. That leaves us with 540,000 people. Okay, and then the following year, an additional 10% of the people left. So 10% of the remaining people left. Okay, so this year, how many people left? 60,000, okay? And so then we're going to find this year, how many people will leave? 54,000, because we have fewer people, so we're taking a percentage of a slightly smaller number. So 540,000 times 90% or times 0.9, how many people are left at the end of that year? 486,000 people. I made this a little too small, so I'm going to write real narrow here. 486,000 people. And then another year passes and 10% of those people leave. So times 0.9 is 437,400. And then another year passes and 10% of those people leave. So times 90% or times 0.9, 393,660 people. Okay, so how many people were there at the end of the year 2011? 540,000. At the end of the year 2012, 486,000. At the end of 2013, 437,400. And at the end of 2014, 393,660 people. So while 10% doesn't sound like a lot, we're getting really, in just 1, 2, 3, 4 years, we're getting pretty close to half of the people leaving. Do you see how powerful that compounding effect is? Okay, that's why we call exponents what? What's the other word we use for them? Power, because it's very powerful, okay? So even though, like, again, I just want to say that again for emphasis, 10% doesn't sound like a lot, right, boys and girls? But if I'm compounding it, it adds up very quickly. It's very powerful, okay, compounding value. So if we started with 600,000 people, but we're losing 10% per year, after just 4 years, we're down to 393,000, okay? Let's see what will happen in one more year. So 1 year later, so just after 5 years, we will have 354,294 people. So it's rapidly decreasing. Okay. Which situation represented growth and which situation represented decay? All right, which one represented growth, everyone? Okay, good. The bank account. And which one represented decay? Good, the population. Okay, so rather than making those tables and having to calculate the each year in order to get the next year, in order to get the next year, in order to get the next year, because we know this each time we're multiplying, for instance, in the population problem, each time we multiplied by 0.9, okay, times 0.9 times 0.9. What is this number called in an exponential function? What is it? The number that we're multiplying by. Remember our parent function was y equals a times b to the x? Which one is that? What's this number that we're multiplying by, this repeated multiplication? It's that b, the base, right, boys and girls? B to a power. How many times did I multiply by 0.9? What does the a stand for? Starting amount. Very good. Okay, so where did I start off with in the beginning? Okay, then how many times did I multiply it by 0.9? Okay, so this is that same formula, but we're going to make it a little bit more complicated because now we are incorporating percentages. Okay, so that's not a whole lot more complicated. The percentage only impacts the growth, the base. Okay, the rate of growth or the rate of decay. So this is going to be very exponential growth and decay functions, right? It's just a type of exponential function. So it's just a type where our base, it starts off with some initial amount, and it's either growing at a rate, or it is decreasing at a rate, or decaying at a rate. Okay, so this looks very similar. Our amount, if you remember, this is what we worked on last week and this week, is equal to our initial amount, A. Here we're calling it the principal amount, the starting amount. It's the same thing, times, this was just a base, but now we're actually having a base that's impacted by some sort of percentage growth or decay. So it's our starting amount plus some percentage or minus some percentage here to the power of t. Okay, here we're just, it's the same, it's an exponent, but in this case it's over time. We're looking at growth or decay over time. So in this scenario, the A represents our total amount. Okay, the P is the principal or the starting amount. This is principal. Okay. The R is our growth rate or decay rate. I'm just going to write rate. We're not going to do this twice. The rate, rate of, we'll do rate of growth. In this case, it'd be rate of decay, written as a decimal. Okay, and T is time, elapsed time. In other words, how much time has passed, elapsed time. Okay, then we're going to look at another scenario. Collector car. Now typically, cars depreciate in value. So 99.9% of cars depreciate in value. The moment you drive a brand new car, the moment you drive it off the lot, it instantly turns into a used car because it's been driven by you. So cars, boats, trucks, campers, snowmobiles, things like that, they depreciate in value. Unless it's a collector item. If it's a special item or a high demand item, it can increase in value. So here is one of those exceptions. We're looking at a collector car. So think Woodward Dream Cruise. The owner of a 1953 Hudson Hornet convertible sold the car at an auction. The owner bought it in 1984 when its value was $11,000. The value of the car appreciates. What does it mean to appreciate when we're talking about money? To grow. Very good. And what's the opposite of appreciating in value? Depreciating. Good. Depreciating in value. The owner of the car, the value of the car appreciates at a rate of 6.7% per year. 6.7% per year. Write a function that models the value of the car over time. And if the auction took place in 2004, what is the approximate value of the car at the time of the auction, round to the nearest dollar? Okay, so let's go ahead and write the function for part A. The amount, or the price of the car, is going to be equal to its initial value. I see he bought it, or she bought it, at $11,000. Times 1. Am I going to have a plus here or a minus? Growth or decay? Growth. Okay, it's appreciating in value. So it's growing in value. What's my growth rate? 6.7%. How do I write that as a decimal? 0.067, right, boys and girls? Because percentage is per 100. So you take this, you divide it by 100. With the decimal once to the left, twice to the left. Okay, 0.067. Now we have to look at the power. The owner bought the car in 1984. So that's where we start our problem. 1984 is going to correspond with year 0. Okay? And then the auction takes place in, oh, sorry, well, I'm kind of jumping ahead here. This is just going to be to the power of t. And then let's calculate what that t is. This auction takes place in 2004. Okay, so that was a little while ago. If the car was bought in 1984 in relation to that being year 0, the starting point, we're looking at how much it'll sell for if it's appreciating at 6.7% per year. How many years have passed, or what is the elapsed time from 1984 to 2004? Good. So it's 2004 minus 1984. 20 years have passed. Okay, so let's go ahead and calculate that. The amount of money is going to be equal to 11,000 times 1 plus 0.067 to the 20th power. Okay, so your function should look like that, or your equation should look like that. 11,000 times 1 plus 0.067. Don't forget your parentheses. Those are located above the 8 and 9 buttons. Raised to the power of, and then your caret key right here, kitty corner from the 7 to get your into the exponent. And how much will it be worth at the end of 20 years? Pretty nice, right? $40,242. Okay, so to the nearest dollar, that's $40,242. Pretty nice little investment, right? Okay. Not so sure that happens most of the time, but that's great that it happened in that case. Now, what about a newer car that's not a special collector car that people are interested in? So we're looking now at a Honda Accord. A 2006 Honda Accord, sold the car to a coworker. The owner bought the Accord originally for $14,560 in 2006. The value of the Accord depreciates at a rate of 8.9% per year. Write a function that models the value of the Accord over time. So do we have appreciation or depreciation here? So we have exponential what? Decay. Good. Okay, so we have the amount of money is going to be equal to the initial purchase price, $14,560, multiplied by the growth decay rate to the time elapsed power. So we had 1 minus, here's our decay rate, sorry that's blurry, 8.9%, so 1 minus 0.089, okay, to the t power. What is the approximate value of the Accord at the time of the sale in 2010? Okay, well, year 2006, we're not going to do it to the 2010 power, okay? 2010 years haven't passed, so we want to know how many years have passed. 2006 corresponds with our starting point, so 2010 corresponds with year what? 4. 2010 minus 2006. 4 years have passed. So we will have A equals 14,560 to the 1 minus 0.089 to the 4th power. Okay, and then they asked us to round to the nearest dollar. So $10,028. So the sale price of the car will be approximately $10,028. Okay, next, compounding interest. Okay, you put $250 into a savings account that earns 4% annual interest compounded yearly, and you leave it alone. Write an equation to model this situation, and then tell me how much your investment will be worth in 5 years. Okay, so our amount is going to be equal to, what's our initial investment, our principal? $250 times 1, and do we have growth or decay? Growth, so plus Okay, exponential growth will always have a base that's higher than 1. Exponential decay, if I'm subtracting, I'll have a base that is less than 1. Okay, so 1 plus 4% to the t power. And then they ask us to tell how much it will be worth in 5 years. So the amount of money will be equal to that same equation to the 5th power. Okay. So you made $54.16 on your investment. All right, then new house. You paid $250,000 for a house in 2004. With the current housing market, the value of your home has decreased 2.35% per year. Now that's not typical. Typically the housing market increases, not always, but typically. So we had a financial, some very bad financial events happening in that time period. So write an equation to model the situation. How much is your house worth in 2010? So our amount of money that our house will be equal to is the principal, which was $250,000, times the 1. And what do we have here? Growth or decay? Good. Minus, because it's decay. What's our decay rate? 2.35%. Good. So minus 0.0235. And they asked us to tell the value in 2010. What was our starting year? 2004 corresponds with our starting time. Okay, so what's 2010 minus 2004? 6 years. Okay, so this is going to be to the 6th power. Okay, so the house that you paid $250,000 for 6 years later is worth $216,757. So that's bad news. So it's the depreciation. Fortunately, the market's bouncing back. Okay. So here's an interesting situation. You are working at a job, and your boss has an odd way of paying the employees. She pays her employee $1 for the first day, and then increases their pay by 25% each day afterward. First, write an equation to model the situation. Then find out how much money will you get paid for that 30th day of work. Okay, so the first day you made $1. How much do you make on day 30? All right, so we have a very high growth rate here. Okay, 25%. So let's write the model. The amount of money is equal to our starting amount. What's our starting salary per day? Or wages? $1 per day? Who wants to work for her? Okay. Times 1. Do we have growth or decay? Is our pay rate going up or down? Up. What percentage? 25%. This is 0.25. And that's going to be to the t power. And then calculate the 30th day. So that'll be equal, the amount of money on the 30th day will be equal to 1. That was your initial daily rate of pay, times 1 plus 0.25 to the 30th power. So how much money are you going to make just on day 30? On day 30, how much do you get paid? $807.79. Oh, that's much better than I made on day 1. $1. How much did I make on day 30? $807.79. I think I'd like to work for her, right? For a long time. Okay. So that would be obviously a very unusual way of paying people, and you'd have to have a whole lot of money to pay your salaries. Okay, so today we learned how to represent real-life situations with exponential growth and decay functions, and we also learned how to evaluate those functions. Okay, and ring your confidence level. How confident are you? On a scale of 1 to 5, and tell me why you have that level of confidence. Okay, nice work, boys and girls.